In 1964, a Soviet astronomer named Nikolai Kardashev was trying to solve a problem. He wanted to detect alien civilizations, but he needed a way to categorize them, to understand what he should even be looking for. His solution was elegantly simple. He proposed measuring civilizations by their energy consumption. After all, whether you're building pyramids or launching rockets, it all comes down to energy. The more energy you can harness, the more advanced you are. He proposed 3 types. Type 1, a civilization that harnesses all the energy available on their planet. Type 2, a civilization that harnesses all the energy of their star. And Type 3, a civilization that harnesses all the energy of their galaxy. It's a neat framework, simple, intuitive, easy to understand. But here's the problem. We're not a Type 1 civilization. We're not even close. According to astronomer Carl Sagan, who later refined the scale to allow for decimal places, humanity in 1973 was a Type 0.7 civilization. As of 2024, we've clawed our way up to approximately Type 0.73. That's right. We haven't even unlocked the first level. We're still in the tutorial stage of cosmic development, and we're struggling with the basic controls. So, what does it actually mean to be stuck at Type 0.73? And more importantly, what would it take to reach Type 1? To answer that, we need to talk about energy. Specifically, how much energy humanity currently uses, where it comes from, and why our current approach is, to put it mildly, embarrassingly primitive. Right now, humanity consumes about 580 exajoules of energy per year. If you don't know what an exajoule is, congratulations on being a normal person. Let me translate that into something more tangible. 1 exajoule equals 1 quintillion joules, which is 1 followed by 18 zeros. It's also about 278 terawatt-hours, or roughly the energy released by 24 megatons of TNT. So, when we say humanity uses 580 exajoules per year, we're saying we consume the energy equivalent of nearly 14,000 megatons of TNT annually. That might sound impressive. It might even sound like a lot, but that number is about to be put into perspective in a way that will make it look absolutely microscopic. Before we get to that gut punch, let's talk about where this energy actually comes from. According to the International Energy Agency, approximately 80% of our energy comes from fossil fuels: coal, oil, and natural gas. Another 10% comes from biomass, which is a fancy way of saying we're burning wood and plant matter. About 5% comes from nuclear fission, and the remaining 5% comes from renewables like solar, wind, hydroelectric, and geothermal. Let's be honest about what this means. We are, by and large, a civilization that powers itself by setting fire to dead organisms that have been compressed underground for millions of years. We dig up ancient plants and animals, we set them on fire, and we use the resulting heat to boil water, which creates steam, which turns turbines, which generate electricity. This is not a joke. This is genuinely how most of our power plants work. We're using technology that would be fundamentally recognizable to someone from the 19th century. Sure, we've made incremental improvements. Modern coal plants are more efficient than Victorian-era ones. But the basic principle remains unchanged. Burn thing, make heat, boil water, spin turbine. It's the same process, just with better materials and computer controls. This is pathetic by Kardashev standards. Imagine if aliens showed up tomorrow and asked to see our energy infrastructure. We'd have to show them power plants that work by lighting things on fire. We'd have to explain that, yes, we know the sun is right there, broadcasting 174 petawatts of free energy at us every single day. But we've decided to mostly ignore that in favor of digging up ancient swamps and setting them ablaze. The aliens would look at our energy grid the way we look at someone trying to power a city by rubbing sticks together. But it gets worse. Not only are we using primitive combustion-based energy, we're using it in a way that's actively destroying the planet we live on. Burning fossil fuels releases carbon dioxide, which traps heat in the atmosphere, which causes global temperatures to rise, which melts ice caps, which raises sea levels, which causes droughts and floods and hurricanes, and a cascade of climate disasters that threaten to destabilize civilization itself. We are, quite literally, poisoning ourselves with our own waste products. It's like heating your house by burning furniture, except the smoke is also making your house collapse. And we know this. We've known this for decades. We have the technology to do better. Solar panels exist. Wind turbines exist. Nuclear reactors exist. And yet, 80% of our energy still comes from fossil fuels, because changing our infrastructure is expensive and politically difficult, and requires global cooperation on a scale we've never achieved. This is the first hint of the problem we're going to keep running into. The bottleneck to becoming a Type 1 civilization isn't technology. It's us. Now, let's talk about what Type 1 actually means in terms of numbers, because this is where things get truly humbling. A Type 1 civilization commands approximately 10 to the power of 16 watts of power. That's 10,000 watts. Or, if you prefer your incomprehensible numbers with prefixes, that's 10 petawatts. For comparison, humanity currently uses about 18 terawatts. A terawatt is 10 to the power of 12 watts. So, we need to increase our energy consumption by a factor of approximately 555. Now, you might be thinking, okay, so we just build 555 times more power plants. Problem solved, right? No, absolutely not, because the real question isn't how do we generate that much energy. The real question is, what the hell are we even doing with that much energy? This is crucial to understand. A Type 1 civilization doesn't just use more energy. They use energy fundamentally differently than we do. They're not just running more air conditioners and charging more phones. They're doing things that require planetary-scale energy expenditure. Things like complete control over the planet's weather and climate. Not we installed some solar panels and feel good about ourselves control. We're talking about the ability to redirect hurricanes, create rain on demand, terraform deserts into forests overnight, prevent ice ages or trigger them if needed, and manage the entire carbon cycle like a thermostat. This requires energy on the scale of planetary weather systems. A single hurricane releases energy equivalent to about 600 terawatts. To control it, we'd need to match or exceed that. A Type 1 civilization also has complete control over plate tectonics. Earthquakes. They can either prevent them by managing stress in fault lines or trigger controlled releases to prevent catastrophic buildups. Volcanoes. They can tap them for geothermal energy on a massive scale or suppress eruptions entirely. This means drilling to depths we currently can't reach, managing pressures we can barely measure, and having a real-time understanding of everything happening inside the entire planet. They also have complete control over the oceans. We're talking about regulating ocean currents to optimize heat distribution, managing sea levels down to the centimeter, eliminating dead zones by precision nutrient management, aquaculture on a scale that makes current fishing look like a child with a net, and extracting minerals from seawater efficiently. And then there's the space infrastructure. At Type 1, humanity is no longer confined to Earth's surface. We have orbital rings or space elevators for routine access to orbit. We have mass drivers launching payloads at a fraction of current costs. We have dozens of O'Neill cylinders in Earth orbit housing millions of people. We have lunar bases with permanent populations in the thousands. We have asteroid mining operations throughout the inner solar system. And yes, we've finally figured out fusion reactors. This is what a Type 1 civilization looks like. And to power all of this, we need 10 petawatts. So when someone asks why we can't just build 555 times more coal plants, the answer is because coal plants can't give you weather control. They can't give you the ability to manage tectonic plates. They can't give you the infrastructure to colonize space. You need fundamentally different technologies and fundamentally different scales of engineering. You need to transition from a civilization that burns dead things for energy to a civilization that harvests energy directly from the sun, from fusion reactions, from the Earth's core, from the fabric of space itself if you can figure out how. This transition is not optional if you want to reach Type 1. It's mandatory. So how did we get here? How did humanity go from rubbing sticks together to consuming 580 exajoules per year? Let's take a brief walk through the history of human energy consumption, because understanding where we came from helps explain why we're stuck where we are. For most of human history, our energy consumption was negligible. Early humans had fire, which provided heat and light and the ability to cook food. They had muscle power, their own, and eventually that of domesticated animals. And that was about it. Energy consumption per person was maybe 2,000 to 3,000 kilocalories per day from food, plus whatever wood they could burn for warmth. This remained essentially unchanged for thousands of years. The invention of agriculture increased food production, which allowed for larger populations, but energy consumption per person stayed roughly the same. Then came the first major shift: wind and water power. Humans learned to harness the kinetic energy of moving air and water to grind grain, pump water, and power simple machinery. Windmills and water wheels multiplied human capability without requiring more human or animal labor. But the real explosion came with the Industrial Revolution in the late 18th and early 19th centuries. The invention of the steam engine allowed humans to convert heat energy into mechanical work on a massive scale. Suddenly, you could power factories with coal-fired boilers. You could drive locomotives and ships. You could do the work of 100 horses with a single machine. Energy consumption skyrocketed. In 1800, total global energy consumption was roughly 20 exajoules per year. By 1900, it had climbed to about 45 exajoules. By 1950, we'd reached 100 exajoules. By 2000, we'd hit 420 exajoules. And by 2024, we're at 580 exajoules. That's nearly a 30-fold increase in just over 2 centuries. This exponential growth has been fueled almost entirely by fossil fuels. Coal powered the Industrial Revolution. Oil powered the 20th century with internal combustion engines and petrochemicals. Natural gas became the fuel of choice for electricity generation and heating. We discovered these dense, energy-rich deposits of ancient organic matter, and we've been burning through them as fast as we can dig them up. But here's the thing about exponential growth. It can't last forever. Not on a finite planet with finite resources. We've already burned through a significant fraction of the easy-to-access fossil fuels. What remains is harder to extract, more expensive, and often located in geopolitically contentious regions. And even if we had unlimited fossil fuels, we couldn't keep burning them at current rates without cooking the planet. we're already seeing the consequences. Global average temperatures have increased by about 1.1 degrees Celsius since pre-industrial times. Ice sheets in Greenland and Antarctica are melting. Sea levels are rising. Extreme weather events are becoming more frequent and more severe. Entire ecosystems are collapsing. And we're on track to hit 1.5 degrees of warming within the next decade or two, which scientists warn is a critical threshold beyond which feedback loops could spiral out of control. So we're stuck. We can't keep growing our energy consumption at 3% per year using fossil fuels without destroying the climate. But we also can't reach Type 1 without massively increasing our energy consumption. This is the trap. This is why we're stuck at Type 0.73. The bottleneck isn't technology. We have solar panels. We have wind turbines. We have the theoretical knowledge to build fusion reactors, even if we haven't quite gotten them to work yet. The bottleneck is coordination. It's politics. It's economics. It's the fact that transitioning away from fossil fuels requires global cooperation on a scale we've never achieved. Let me give you some examples of how badly we're failing at this. The Paris Agreement, signed in 2015, was supposed to unite the world in the fight against climate change. Countries pledged to limit global warming to well below 2 degrees Celsius. It was hailed as a historic moment of international cooperation. As of 2024, almost no major country is on track to meet their pledges. Global carbon emissions continue to rise. We keep building new coal plants, new oil pipelines, new natural gas terminals. We keep subsidizing fossil fuel companies to the tune of hundreds of billions of dollars per year. We know what needs to be done. We know that we need to rapidly transition to renewable energy. We know that we need to electrify transportation. We know that we need to develop better energy storage technology. We know that we need to invest in research and development for fusion power and next-generation nuclear reactors. We know all of this. And yet, we're not doing it fast enough because it's expensive, because it threatens existing power structures, because fossil fuel companies have enormous political influence, because people don't want to change their lifestyles, because developing countries argue that rich countries got to develop using cheap fossil fuels. So why shouldn't they? Because the benefits of action are long-term and diffuse, while the costs are immediate and concentrated. This is the fundamental problem. A Type 1 civilization requires planetary-scale coordination. It requires humanity to act as a single coherent entity with shared goals and shared sacrifice. It requires us to think in terms of centuries, not election cycles. It requires us to prioritize the survival and flourishing of our species over short-term profits and national interests. And we are spectacularly bad at this. We can't even agree on basic facts. We have people who deny that climate change is happening. We have people who acknowledge it's happening, but deny that humans are causing it. We have people who acknowledge humans are causing it, but argue we shouldn't do anything about it, because the economic costs are too high. We have people who want to do something about it, but can't agree on what. We are a species that struggles to cooperate within our own nations, let alone across national borders. We fight wars over resources, over ideology, over territory, over religion, over historical grievances. We have nuclear weapons pointed at each other. We have massive wealth inequality. We have authoritarian governments and failing democracies and corruption and tribalism and short-sighted thinking everywhere you look. And somehow, we're supposed to coordinate well enough to transition our entire global energy infrastructure, manage the climate of an entire planet, and build the space infrastructure necessary to reach Type 1. The pessimists would say it's impossible. They'd say we're going to burn through our fossil fuels, overshoot our climate targets, trigger runaway warming, and collapse back to a pre-industrial or even pre-agricultural state. They'd say the Great Filter, that hypothetical barrier that prevents civilizations from becoming spacefaring, is right here, right at the Type 0.7 to Type 1 transition. They'd say that's why we don't see any aliens. They all killed themselves at this stage, just like we're about to. The optimists would say we can do it. They'd point to the fact that solar and wind are now cheaper than fossil fuels in many places. They'd point to the rapid development of battery technology. They'd point to the younger generation that seems more aware of climate issues and more willing to demand action. They'd point to the fact that we've solved seemingly impossible coordination problems before. We eliminated smallpox. We closed the ozone hole. We've built international institutions that, while imperfect, at least provide forums for cooperation. They'd say we have the technology and the knowledge. We just need the political will. And the realists would say we're probably going to muddle through. We won't take the bold, coordinated action we need, so we'll suffer more climate disasters than necessary. We'll have more conflicts over resources. We'll have more inequality and suffering. But we probably won't go completely extinct. We'll limp along, making incremental progress, taking 2 steps forward and 1 step back, and maybe, if we're lucky and persistent and just barely competent enough, we'll eventually stumble our way to Type 1. In a few hundred years. Maybe. If everything goes right. Which brings us to the central question of this entire documentary. Can we even get to Type 1 without destroying ourselves? The answer is we don't know. We genuinely don't know. We're the first civilization on Earth to reach this level of technological development. We have no precedent. We have no roadmap. We're making this up as we go along. And the stakes couldn't be higher because if we fail, that's it. Humanity doesn't get a second chance. We burn through our fossil fuels once. We get one shot at building a sustainable energy infrastructure before climate change makes it exponentially harder. We have one opportunity to prove that intelligent life can make it past the Type 0.7 trap. And right now, we're failing. We're stuck. We're a Type 0.73 civilization with Type 1 dreams and Type 0.5 cooperation skills. But we're not dead yet. And as long as we're not dead, there's a chance. A slim chance. A non-zero chance. So let's talk about what it would actually take to get to Type 1. Let's talk about the technologies, the infrastructure, the engineering challenges, and the sheer scale of what we'd need to build. Because maybe, just maybe, understanding what we need to do is the first step toward actually doing it. So let's talk about what a Type 1 civilization actually looks like, because this is where most people get it wrong. They think Type 1 just means we have more power plants, bigger solar farms, more nuclear reactors. They think it's a quantitative difference, not a qualitative one. They're wrong. A Type 1 civilization doesn't just use more energy. It uses energy in fundamentally different ways. Ways that would look like magic to us today. Ways that would completely reshape what it means to be human on Earth. Let me give you some examples. Complete control over the planet's weather and climate. And I don't mean we installed some solar panels and feel good about ourselves. Control, I mean the ability to redirect hurricanes, to create rain on demand anywhere on the planet, to terraform deserts into forests overnight, to prevent ice ages or trigger them if needed, to manage the entire carbon cycle like you manage the thermostat in your house. This isn't science fiction. This is just applied physics at a scale we haven't achieved yet. A hurricane releases energy equivalent to about 600 terawatts. If you can generate and direct energy on that scale, you can steer it, weaken it, or dissipate it entirely. You could inject ions into the atmosphere to alter pressure systems. You could deploy orbital mirrors to heat or cool specific regions. You could manage global wind patterns by controlling temperature differentials. The technology to do this doesn't violate any laws of physics. We just don't have the infrastructure or the energy budget to pull it off. But a Type 1 civilization does. They can look at an approaching hurricane and simply decide it's not going to hit that city today. They can look at a drought-stricken region and decide it's going to rain tomorrow. They can manage the climate of the entire planet the way we manage the temperature in a greenhouse. Then there's tectonic management. Control over earthquakes and volcanoes. Right now, we can predict earthquakes maybe seconds or minutes before they happen. We can monitor volcanoes and evacuate people when eruptions seem imminent. But we can't do anything about them. A Type 1 civilization can. They can drill deep into fault lines and either relieve stress gradually to prevent catastrophic quakes, or they can reinforce regions to prevent movement entirely. They can tap volcanic systems for geothermal energy on a massive scale, extracting heat from the mantle and using it to power entire continents. Or they can suppress volcanic activity if needed, preventing eruptions that would otherwise devastate populated areas. This requires drilling to depths we currently can't reach. The deepest hole ever drilled, the Kola superdeep borehole in Russia, only made it 12 kilometers down. The Earth's mantle starts at about 35 kilometers under continents and 7 kilometers under oceans. To manage tectonic activity, you need to drill 50, 100, maybe 150 kilometers down. You need materials that can withstand temperatures of over 1,000 degrees Celsius and pressures that would crush any current drilling equipment like a soda can. You need real-time monitoring of stress and temperature across the entire planet. You need computer models that can predict tectonic behavior months or years in advance. And you need the energy to actually do something about it. All of this is theoretically possible. We just need about 1,000 times more capability than we currently have. Ocean management is another piece of the puzzle. A Type 1 civilization doesn't just fish the oceans. They manage them. They regulate ocean currents to optimize heat distribution around the planet. They manage sea levels down to the centimeter by controlling ice sheet melting and formation. They eliminate dead zones by precision nutrient management, monitoring oxygen and chemical levels in real time and adjusting them as needed. They practice aquaculture on a scale that makes current fishing look like a child with a net in a pond. They are farming the oceans the way we farm land, with the same level of control and optimization. And they're extracting minerals from seawater. There's gold in seawater. Not much, about 13 billionths of a gram per liter, but it adds up. There's also lithium, uranium, magnesium, and a host of other valuable elements. Right now, extraction costs are higher than the value of what you extract. But with cheap enough energy and efficient enough technology, you could mine the oceans for materials instead of tearing up the land. A Type 1 civilization does all of this simultaneously. They're not managing weather or oceans or tectonics separately. They're managing the entire planet as a single integrated system, because everything is connected. Ocean currents affect weather patterns. Tectonic activity affects ocean chemistry. climate affects tectonic stress through ice sheet loading. You can't manage one without managing all of them. This is what Type 1 actually means: planetary scale systems engineering. And to power all of this, you need 10 petawatts. So, how do you actually generate 10 petawatts? Let's break down the realistic options, and I want to emphasize realistic because we're not going to talk about zero-point energy or vacuum, fluctuations, or any other speculative physics. We're going to talk about technologies we understand, even if we can't build them yet. First option, solar power. The Earth receives approximately 174 petawatts of solar energy. We only need 10 of that. That's less than 6%. Sounds easy, right? Just cover 6% of Earth's surface with solar panels. Earth's surface area is 510 million square kilometers. 6% of that is 30.6 million square kilometers. For reference, that's larger than the entire continent of Africa. Even if we only covered deserts, we'd need to carpet the Sahara, the Arabian Desert, the Gobi, the Kalahari, and the Australian outback combined with solar panels. And that's assuming 100% efficient panels. We're currently at about 22% efficiency for commercial panels. So, realistically, you'd need to cover an area closer to the size of Asia. And you'd need perfect energy storage, which we don't have. You'd need zero transmission losses, which is physically impossible. You'd need to deal with dust, sandstorms, degradation, and maintenance across tens of millions of square kilometers. It's technically possible, but it's a nightmare. The better approach is space-based solar power. Put massive solar arrays in orbit where there's no weather, no nighttime, and no atmosphere absorbing energy. Beam the power down to Earth via microwave or laser to receiving stations on the ground. This solves most of the problems with ground-based solar. To generate 10 petawatts from space, you'd need approximately 35,000 satellites the size of the International Space Station. Each one would mass about 420 tons. That's a total of 14.7 million tons of material in orbit. For comparison, the total mass of everything humanity has ever launched into space is about 10,000 tons. So, you need to increase that by a factor of 170. This is why you can't just rocket your way to Type 1. At current launch costs of around $500 per kilogram to orbit, putting 14.7 million tons up there would cost $22 trillion. That's about 20% of global GDP, just for launch costs, not including construction, operation, or maintenance. You need to bring launch costs down by at least 2 orders of magnitude, which means you need space elevators, orbital rings, or mass drivers. We'll get to those in a moment. Second option, fusion power. Fusion is the holy grail of energy generation. It's what powers the sun. You take light elements like hydrogen isotopes, you smash them together hard enough, and they fuse into heavier elements, releasing enormous amounts of energy in the process. The fuel is abundant. Deuterium can be extracted from seawater. Tritium can be bred from lithium. The waste products are non-radioactive. There's no meltdown risk like with fission reactors. It's clean, safe, and effectively unlimited. We've been trying to make it work since the 1950s. We've been promised it's only 30 years away for 70 years now, but let's assume we finally crack it. What would it take to generate 10 petawatts from fusion? Deuterium-tritium fusion, the easiest reaction to achieve, produces about 17.6 million electron volts per reaction. If you do the math and convert that to watts, you'd need approximately 10 million fusion reactors, each producing 1 gigawatt of power. For comparison, We currently have about 440 fission reactors worldwide, producing a combined 400 gigawatts. So, we'd need to build 25,000 times more fusion reactors than we currently have fission reactors. Each reactor would need fuel. For deuterium-tritium fusion at this scale, you'd need about 200,000 tons of deuterium per year and 300,000 tons of tritium per year. Deuterium is abundant in seawater, not a problem. Tritium doesn't exist naturally in useful quantities. You have to breed it from lithium inside the fusion reactor itself. Earth has about 14 million tons of lithium reserves. At a consumption rate of 300,000 tons per year, we'd run out in 46 years. So you'd need to mine the moon or asteroids for lithium. Which brings us back to space infrastructure. You can't do Type 1 from Earth's surface alone. Third option, deep geothermal. The Earth's core is about 6,000 degrees Celsius. There's an enormous amount of heat energy down there. Currently, we tap geothermal energy from relatively shallow sources, a few kilometers down where there are convenient pockets of hot water or steam. But what if we drilled deep? Really deep. To generate 10 petawatts from geothermal, you would need approximately 100,000 boreholes, each 50 to 100 kilometers deep, each producing about 100 megawatts. The deepest hole we've ever drilled made it to 12 kilometers before we gave up. To drill to 100 kilometers, you'd need materials that can withstand over 1,000 degrees Celsius under crushing pressure. You'd need cooling systems to prevent your drilling equipment from melting. You'd need a complete revolution in drilling technology. But it's not impossible. It's just hard. Really, really hard. Realistically, a Type 1 civilization wouldn't rely on just one energy source. They'd use a combination. Maybe 40% space-based solar, 4 petawatts. Maybe 30% fusion, 3 petawatts. Maybe 15% deep geothermal, 1.5 petawatts. Maybe 10% from conventional renewables like wind and hydro, 1 petawatt. And maybe 5% from matter-antimatter annihilation for specialized applications like interplanetary spacecraft, 500 terawatts. Yes, antimatter. At Type 1, you've probably figured out how to produce and store it efficiently. You need it for deep space missions anyway, because chemical rockets just don't cut it once you're trying to reach the outer planets in reasonable timeframes. This is the energy generation infrastructure of a Type 1 civilization. Tens of thousands of space-based solar satellites, 10 million fusion reactors, 100,000 ultra-deep geothermal wells, antimatter production facilities, a global energy grid that can route petawatts of power from one side of the planet to the other with minimal loss. And all of this requires space infrastructure that makes the International Space Station look like a toy. Let's talk about why you absolutely must industrialize space to reach Type 1. It's not optional, it's not a nice-to-have, it's mandatory. Here's why. First, you need cheap access to orbit. Really cheap. As in 2 orders of magnitude cheaper than current costs. There are 3 main approaches that could achieve this: space elevators, orbital rings, and mass drivers. A space elevator is exactly what it sounds like. A cable extending from Earth's surface to geostationary orbit at 36,000 kilometers altitude. You attach a climber to the cable and it rides up to space powered by lasers or electricity transmitted through the cable itself. No rockets required. The problem is the cable. It needs to support its own weight plus the weight of climbers plus a safety margin. No known material is strong enough. Carbon nanotubes might work, but we can't manufacture them in the required lengths or purity yet. So, space elevators are theoretically possible but practically difficult with current technology. An orbital ring is different. It's a massive ring structure encircling the Earth, typically at low orbit, maybe 200 to 300 kilometers up. The ring itself rotates at orbital velocity, while a stationary structure hangs down to the surface supported by magnetic levitation. You take an elevator up to the ring, then transfer to vehicles that accelerate along the ring to reach escape velocity. Building an orbital ring requires launching about 10 million tons of material into orbit. That sounds impossible, but here's the trick. You build a smaller ring first using conventional rockets. Then you use that ring to launch materials for a bigger ring more cheaply. Then you use the bigger ring to build an even bigger one. It's a bootstrapping process. The first ring is expensive. Every ring after that gets cheaper. Within a few decades, you could reduce launch costs from $1,500 per kilogram to about $10 per kilogram. Mass drivers are the third option. Essentially, they are giant electromagnetic catapults. You put your payload in a cradle, and powerful magnets accelerate it down a track until it's moving fast enough to reach orbit. The track needs to be long, maybe 100 kilometers, and it needs to be built on a mountain or in a tunnel to minimize atmospheric drag. And your payload needs to survive accelerations of 10 to 30 Gs, so no humans. But for bulk materials, it works fine. You could launch millions of tons of raw materials into orbit for pennies per kilogram. The Moon is an ideal location for a mass driver because there's no atmosphere and lower gravity. You could build a track just a few kilometers long and launch payloads to Earth orbit or to construction sites throughout the solar system. Once you have cheap access to space, you can build O'Neill cylinders. These are rotating, space habitats that provide Earth-like gravity through centrifugal force. The classic design is 32 kilometers long and 6.4 kilometers in diameter. It rotates at 1 revolution per minute, which produces 1 G of artificial gravity on the inner surface. Inside, you have a breathable atmosphere, forests, lakes, houses, entire cities built on the inner wall. It looks like you're living inside a giant curved valley that extends up and over your head. From the ground, you can look up and see the other side of the cylinder above you, complete with clouds and sky. An O'Neill cylinder of this size can comfortably house about 10 million people. To build one, you need approximately 10 billion tons of material. That's where asteroid mining comes in. You don't launch that much mass from Earth. You mine it from asteroids and process it in space. A single metallic asteroid a few kilometers across contains more iron, nickel, platinum, and rare earth elements than humanity has mined in all of history. You send autonomous mining robots to the asteroid belt. They extract materials, refine them on site, and send processed metals to construction sites in Earth, orbit, or at the Lagrange points. At Type 1, you probably have 10 to 20 O'Neill cylinders, housing 100 to 200 million people off Earth. You have a permanent lunar population of 10 to 50 million. The Moon becomes humanity's industrial center because it has low gravity, no atmosphere, and abundant raw materials. You build your solar panel arrays there. You launch materials from there using mass drivers. You mine helium-3 for fusion reactors. You set up radio telescope arrays on the far side where there's no interference from Earth's radio noise. The Moon at Type 1 looks nothing like the barren rock we see today. It's covered with domed cities, mining operations, manufacturing facilities, and railgun launchers firing payloads into space every few minutes. This is why you can't separate Type 1 energy generation from space infrastructure. To build the solar satellites, you need cheap launch capability. To get cheap launch capability, you need orbital rings or mass drivers. To build those, you need materials from asteroids. To mine asteroids, you need fusion-powered spacecraft. To build fusion reactors, you need lithium from the moon. Everything is interconnected. You can't do one piece without the others. So, what is a Type 1 civilization actually doing with 10 petawatts of power? Let's paint a picture. On Earth, most people live in arcologies. These are self-contained megastructures that are part building, part ecosystem. Paolo Soleri's original arcology concept called for buildings housing 2 million people in structures 3 kilometers tall. At Type 1, you'd probably have dozens of these. Each one requires 50 to 100 gigawatts of power, equivalent to the electrical consumption of a large nation today. Inside an arcology, everything is recycled. Water is purified and reused indefinitely. Waste is broken down and converted into usable materials. Food is grown in vertical farms integrated into the structure. The climate is controlled to be perfect year-round. Transportation is automated and efficient. You have maglev trains connecting different sections of the arcology and connecting arcologies to each other. Most people rarely need to leave because everything you need is within a short transit ride. Work, entertainment, nature, all of it accessible within the same structure. It sounds dystopian when I describe it like that, but it's actually the opposite. By concentrating population density in arcologies, you minimize humanity's footprint on the rest of the planet. You can rewild vast areas of Earth, letting forests regrow, letting animal populations recover. You can have the best of both worlds, high-tech urban living for those who want it, and pristine wilderness for those who don't. Between the arcologies, you have weather control networks. Thousands of installations around the planet capable of injecting ions into the atmosphere to steer storms, deploying orbital mirrors to heat or cool regions, and managing the global water cycle with precision. Each installation requires 10 to 50 gigawatts during operation. The network is managed by artificial intelligence because the number of variables involved is too complex for human oversight. You have atmospheric sensors, ocean buoys, satellite data, and ground stations feeding real-time information into climate models that predict weather patterns months in advance. The AI makes micro-adjustments constantly, preventing droughts, floods, and temperature extremes before they can develop. Then there's the computational infrastructure. At Type 1, you've likely developed artificial general intelligence and possibly superintelligence. The global computer network supporting this requires computational power that dwarfs anything we can imagine today. You have exascale computers in every major population center. You have quantum computing arrays for specialized calculations like protein folding, material science, and cryptography. You have neural networks managing everything from traffic to weather to the power grid. The planetary internet operates at exabit per second speeds. Data centers consume easily 500 terawatts just for computation and communication. The Internet of Things isn't a buzzword anymore. It's everything. Every device, every sensor, every vehicle, every building is connected and feeding data into the global network. The AI manages logistics with perfect efficiency. Food is produced exactly where and when it's needed. Energy is routed to wherever demand is highest. Resources are allocated to minimize waste. It's a planned economy that actually works because the planner is an intelligence far beyond human capability and far beyond human biases and corruption. Of course, this raises questions about control and autonomy And what happens if the AI decides it knows better than humans what humans need? But those are philosophical problems for a Type 1 civilization to solve. The point is, all of this computation requires enormous amounts of energy. In space, you have the O'Neill cylinders I mentioned earlier, but you also have lunar industry. The moon at Type 1 is unrecognizable. Domed cities house millions of people. Sprawling solar farms cover the surface, generating power and beaming it to Earth. Electromagnetic catapults launch refined materials into space every few minutes. Tunnels extend kilometers underground, where mining robots extract helium-3, aluminum, titanium, and rare Earth elements. The far side of the Moon hosts the largest radio telescope array in the solar system because it's shielded from Earth's radio interference. Astronomers there can detect signals from the most distant galaxies with unprecedented clarity. And throughout the inner solar system, you have asteroid mining operations, thousands of autonomous spacecraft, each powered by fusion or antimatter drives, traveling to asteroids, extracting materials, refining them on site, and sending processed metals back to construction yards in Earth orbit or at Lagrange points. Some asteroids are hollowed out and converted into habitats themselves. You spin them up for artificial gravity, seal them, fill them with air, and suddenly you have a ready-made space station with radiation shielding provided by kilometers of rock. This is Type 1. This is what a civilization that has mastered its planet and its local space looks like. And the important thing to understand is that none of this violates physics. None of this requires magic or wishful thinking. It's all engineering. Difficult engineering, yes. Engineering on a scale we've never attempted, but not impossible engineering. The question is, how long does it take to get there? Carl Sagan estimated that at our current rate of energy consumption growth, about 3% per year, we'd reach Type 1 in approximately 100 to 200 years. That sounds optimistic. Really optimistic, because our current growth rate is fueled by burning fossil fuels, and we can't sustain that for another 2 centuries without rendering the planet uninhabitable. So the timeline splits into 3 scenarios. The optimistic scenario says 150 to 200 years. In this scenario, we transition to renewables and fusion by 2050. We manage to avoid the worst effects of climate change through a combination of emissions reductions and geoengineering. Space infrastructure development accelerates by 2100 with the first orbital rings or space elevators coming online. We build the first O'Neill cylinders by 2150, and we achieve full Type 1 status by 2200. This requires everything to go right. It requires unprecedented global cooperation. It requires technological breakthroughs in fusion, materials science, and AI. It requires political will that we currently don't have. But it's not impossible. The realistic scenario says 300 to 500 years. In this scenario, we don't get our act together in time to prevent serious climate damage. We spend the 21st century dealing with the consequences of our fossil fuel addiction. Rising sea levels, mass migration, resource conflicts, periodic economic collapses. But we don't go extinct. We muddle through. We make incremental progress on renewable energy. We slowly build up space infrastructure. We have setbacks, but we also have successes. By 2200, we've stabilized the climate and begun serious space industrialization. By 2300, we have orbital rings and lunar colonies. By 2400 to 2600, we finally achieve Type 1. It's slower, messier, and more painful than the optimistic scenario, but we get there eventually. The pessimistic scenario says never. In this scenario, climate change causes civilizational collapse, or we have a nuclear war that sets us back centuries, or the AI alignment problem goes very badly, and a superintelligent AI decides humans are an obstacle to its goals, or a pandemic worse than COVID sweeps the planet, or we simply never manage to cooperate well enough to make the transition, and we stagnate at type 0.7 or 0.8, burning through our remaining resources until we collapse back to a pre-industrial state. In this scenario, we join the long list of extinct species that once inhabited this planet. The fossil record will show that for a brief moment in geological time, there was a species capable of understanding the universe, and then it was gone. Which scenario is most likely? Nobody knows. We're making this up as we go. But here's what we do know. The bottleneck is not technology. The bottleneck is cooperation. We have the knowledge to build solar panels and wind turbines. We understand the physics of fusion even if we haven't perfected the engineering. We know how to build space elevators and orbital rings in theory. We have the blueprints. What we don't have is the political will to actually do it. We don't have the global institutions capable of coordinating planetary-scale projects. We don't have the ability to think in terms of centuries rather than quarterly earnings reports. We can't even agree to stop burning coal, and we're supposed to coordinate the construction of orbital rings and the management of planetary climate. The problem isn't that we lack the capability. The problem is that we lack the wisdom to use the capability we have. We're a species with the knowledge of gods and the wisdom of children. And that's why reaching Type 1 is genuinely uncertain. It's not a question of can we do it, it's a question of will we do it. Will we choose long-term survival over short-term comfort? Will we choose cooperation over competition? Will we choose to think of ourselves as one species on one planet, rather than a collection of tribes fighting over scraps? Because if we can't make those choices, then Type 1 remains forever out of reach, and we'll be stuck at Type 0.73 until we burn through our resources and collapse. But if we can make those choices, if we can cooperate and sacrifice and think long-term, then Type 1 is achievable. Difficult? Yes. The work of centuries? Yes. But achievable. And that's the choice facing humanity right now, not in some distant future. Right now. Every decision we make about energy, about climate, about space, about cooperation is a decision about whether we reach Type 1 or whether we don't. So, what's it going to be? Let's say we made it. Let's say humanity somehow managed to not destroy itself during the Type 0.7 to Type 1 transition. We've got fusion power, space elevators, O'Neill cylinders, weather control, and a functioning planetary government that can actually coordinate large-scale projects. We've graduated from planetary civilization to proper solar system civilization. We're managing Earth's climate, mining asteroids, and living comfortably with 10 petawatts of power at our disposal. Now what? Well, at some point, probably a few centuries into our Type 1 existence, we're going to hit a wall. There's only so much energy available on and around Earth. Even if we covered every available surface with solar panels, tapped every geothermal source, and built fusion reactors on every celestial body in the inner solar system, we'd eventually max out. To keep growing, we need to go bigger. Much, much bigger. We need to harvest the sun itself. Welcome to Type 2. A Type 2 civilization commands approximately 10 to the power of 26 watts of power. That's 100,000 watts. Or, if you want to put a name to your existential dread, that's 100 septillion watts. Let me put that in perspective. The Sun outputs about 3.8 times 10 to the 26 watts. To qualify as Type 2, we need to harness about 26% of that. Though, let's be honest, if we're going full Type 2, we're harvesting the entire Sun. Anything less is just Type 1 with extra steps. For comparison, Type 1 was 10 petawatts. Type 2 is 10 billion petawatts. That's not a typo. Type 2 uses 10 billion times more energy than Type 1. This is not an incremental step. This is not just building more of what we already have. This is a fundamental transformation in what it means to be a civilization. At Type 1, we mastered our planet. At Type 2, we master our star. And to understand what that means, we need to talk about the single most iconic megastructure in science fiction, the Dyson sphere. In 1960, physicist Freeman Dyson published a paper titled "Search for Artificial Stellar Sources of Infrared Radiation." His argument was elegantly simple. Any advanced civilization will have growing energy needs. The most abundant source of energy in any solar system is the star itself. Therefore, an advanced civilization would eventually build structures to capture as much of their star's energy output as possible. Other astronomers looking for alien civilizations should search for stars that emit unusually high levels of infrared radiation, which would indicate the presence of these energy-collecting structures. This concept became known as a Dyson sphere. But here's the thing that most people get wrong. Dyson never proposed a solid shell around the Sun. That's the pop culture version, immortalized by Star Trek and countless science fiction novels. What Dyson actually proposed was a swarm or shell of many independent structures orbiting the star, collectively capturing most of its output. The distinction matters because a solid shell is physically impossible. And I don't mean difficult. I don't mean we'd need advanced materials or clever engineering. I mean it violates basic physics in ways that no amount of technology can overcome. Let me explain why. Problem 1: gravity. A rigid shell surrounding a star has no net gravitational force holding it in place. This is a consequence of something called the shell theorem, which states that a spherically symmetric shell of matter exerts no net gravitational force on objects inside it. The gravitational pulls from all directions cancel out. What this means is that a Dyson shell would be gravitationally neutral with respect to the Sun. There's nothing holding it in position. Any tiny perturbation, a solar flare, a micrometeorite impact, literally anything, would cause the shell to start drifting. And once it starts drifting, there's nothing to stop it. It would drift until it collides with the Sun. You might think, well, we'll just use thrusters to keep it in place. Active station keeping. Sure. Except you'd need thrusters on a structure with a surface area of 2.8 times 10 to the 17th square kilometers. That's 280 quadrillion square kilometers. Even if you placed one thruster every 1,000 square kilometers, you'd need 280 trillion thrusters, and they'd need to run continuously, fighting against every solar flare, every gravitational perturbation, every tiny push from the solar wind. The energy cost of keeping a Dyson shell in place would be enormous. You'd need a significant fraction of the energy you're collecting, just to prevent the shell from crashing into the Sun. At which point, what's the point? Problem 2: materials. Let's say we ignore the gravity problem for a moment. Let's calculate what it would take to build a solid shell. To build a shell at 1 astronomical unit, that's Earth's orbital distance of 150 million kilometers, you'd need a sphere with a radius of 150 million kilometers. The surface area is 4 pi r squared, which gives us 2.8 times 10 to the 17th square kilometers. Even if we made it just 1 meter thick, we would need 2.8 times 10 to the 17th cubic meters of material. Assuming a density similar to steel, that's about 2.2 times 10 to the 18th tons. For comparison, the entire mass of Earth is 6 times 10 to the 21 tons. So we'd need to disassemble about 0.04% of Earth to build a 1 meter thick shell. That's actually not terrible. The problem is that 1 meter of steel is nowhere near strong enough. The shell would need to support its own weight against tidal forces from the sun. You'd need a shell hundreds or thousands of meters thick, made from materials far stronger than steel. And those materials need to withstand temperatures of thousands of degrees on the sunward side, resist constant bombardment from solar wind and radiation, and not buckle, crack, or deform under structural loads that would make a civil engineer weep. No known material can do this. Not steel, not carbon nanotubes, not graphene, not anything we've ever created or theorized. You'd need materials with strength-to-weight ratios that exceed anything allowed by atomic bonds. It's not a matter of better engineering. It's a matter of physics saying no. Problem 3. Heat. Any structure collecting the sun's energy needs to radiate that energy away. This is basic thermodynamics. Energy in equals energy out, or the structure heats up until it does. A Dyson shell at 1 AU would absorb about 300 watts per square meter. Using the Stefan-Boltzmann law, which governs blackbody radiation, we can calculate the equilibrium temperature. A shell at 1 AU would heat up to about 400 Kelvin, which is 127 degrees Celsius. That's hot enough to make the entire inner surface uninhabitable without massive cooling systems. And where do you radiate the heat to? The outer surface of the shell, which means the outer surface needs to be cool enough to radiate efficiently, but the inner surface is being constantly bombarded by sunlight. You'd need active heat transfer systems moving thermal energy from the inner surface to the outer surface across the entire shell. Pumps, coolant, radiators, all operating continuously on a structure the size of Earth's orbit. The energy cost of this would be staggering. You'd be using a significant fraction of the energy you collect just to keep the shell from melting. Once again, what's the point? So to summarize, a solid Dyson shell is impossible because it has no gravitational stability, requires impossible materials, and faces insurmountable thermal management problems. This is why Freeman Dyson never proposed one. What he proposed, and what any sane Type II civilization would actually build, is a Dyson swarm. A Dyson swarm consists of millions or billions of independent satellites orbiting the star. Each satellite collects solar energy and beams it via microwave or laser to collection points, either on planets, moons, or dedicated receiving stations. The satellites don't form a solid shell. They're in various orbits at various distances, collectively capturing a large fraction of the star's output without requiring impossible materials or active station keeping for the entire structure. So, what does a Dyson swarm actually look like? Let's start with the basic unit, a solar collector satellite. Each satellite would be approximately 1 to 10 square kilometers in surface area. That's roughly the size of a small town. It would mass somewhere between 10,000 and 100,000 tons depending on design and materials. The satellite collects solar energy using either photovoltaic panels or heat engines, converts it to electricity, and then beams it to collection stations using microwave transmitters or lasers. Each satellite would be autonomous, with onboard navigation and station keeping to maintain its orbit and avoid collisions. To capture a significant fraction of the Sun's output, let's say 50%, you'd need millions of these satellites. Let's do the math. The Sun outputs 3.8 times 10 to the 26 watts. We want to capture 50%, so 1.9 times 10 to the 26 watts. Each satellite at 1 AU receives about 1,300 watts per square meter. A satellite with a collecting area of 5 square kilometers, that's 5 million square meters, collects about 6.5 gigawatts. To collect 1.9 times 10 to the 26 watts, you'd need approximately 30 trillion satellites. Each satellite masses about 50,000 tons on average. Total mass, 1.5 times 10 to the 18 tons. For comparison, that's about 250 times the mass of all humans who have ever lived, or about 0.025% of Earth's mass, or about 3 times the mass of the asteroid Ceres. Where do you get that much material? You don't mine it from Earth. You'd strip the planet bare and still not have enough. You mine it from Mercury. Mercury is the obvious choice for several reasons. First, it's close to the Sun, which means short travel times for construction materials. Second, it's small and has low gravity, which makes mining and launching materials relatively easy. Third, it has no atmosphere, no biosphere, and no sentimental value. Nobody cares if you disassemble Mercury. And fourth, Mercury is almost pure metal. Its core is enormous relative to its size, composed mostly of iron with some nickel and trace elements. It's basically a giant ball of raw materials waiting to be turned into solar collectors. Mercury's mass is about 3.3 times 10 to the 23 tons. We need 1.5 times 10 to the 18 tons for the Dyson swarm. That's about 0.05% of Mercury's mass, so you don't even need to disassemble the whole planet. Just strip mine the surface and upper mantle for a few centuries, and you're good. Of course, strip mining an entire planet is easier said than done. You need infrastructure. Lots of infrastructure. You need mining robots, smelters, refineries, factories, and launch systems, all operating on Mercury's surface in an environment where daytime temperatures reach 430 degrees Celsius and nighttime temperatures drop to minus 180 degrees. You need to build all of this autonomously because no human is going to live on Mercury during the construction process. So you send self-replicating robots, von Neumann machines, named after mathematician John von Neumann, who first theorized them. These are robots that can mine raw materials, refine them, manufacture components, and build copies of themselves. You send an initial seed population of maybe a few thousand robots. They land on Mercury, start mining, and begin replicating. Each robot builds 1 or 2 copies of itself, then those copies build more copies, and so on. Exponential growth. Within a few decades, you have millions of robots. Within a century, you have trillions. These robots mine Mercury's surface, extract metals, refine them in solar-powered smelters, and construct solar collector satellites. Electromagnetic catapults, similar to the mass drivers we discussed for the Moon, launch completed satellites into orbit. Because Mercury has low gravity and no atmosphere, you can build relatively short launch tracks and achieve orbital velocity with minimal energy expenditure. The satellites are launched continuously, thousands per day, gradually building up the swarm. How long does this take? Estimates vary, but most studies suggest somewhere between 100 and 500 years to build a partial Dyson swarm, capturing 10 to 50% of the Sun's output. A complete swarm capturing over 90% could take 1,000 years or more. This assumes you're starting from a solid Type 1 foundation with fusion power, self-replicating robots, and the industrial capacity to support this kind of project. If you're still struggling with Type 1 problems, add a few more centuries to the timeline. So, what is humanity doing during this centuries-long construction project? Living in O'Neill cylinders, mostly. By the time you're building a Dyson swarm, Earth is probably a nature preserve. Most humans live in artificial habitats scattered throughout the solar system. You've got millions or billions of people in O'Neill cylinders at the Lagrange points. You've got populations on the moons of Jupiter and Saturn, living in domed cities and extracting resources from those systems. You've got research outposts throughout the solar system studying everything from planetary formation to exotic physics. And you've got a growing population of post-biological humans. By Type 2, the distinction between biological and artificial intelligence has probably blurred or disappeared entirely. Some people upload their consciousness into computer substrates. Some merge with AI systems to become cyborgs. Some stay biological, but with extensive genetic modifications and life extension treatments that render them effectively immortal. The concept of what it means to be human becomes very fluid at Type 2. But let's get back to the megastructures. A Dyson swarm is just one option for a Type 2 civilization. There are others, each with different purposes and engineering challenges. Let's talk about a few. First, the Dyson bubble. This is similar to a Dyson swarm, but instead of satellites in conventional orbits, you use solar sails. These are enormous ultra-thin reflective sheets, maybe a few atoms thick, held in place by radiation pressure from the sun. The sunlight hitting the sail pushes it outward, and if you angle the sail correctly, the outward radiation pressure can balance the inward gravitational pull, creating a stationary position. You could surround the sun with a bubble of stationary solar sails, each one collecting energy and beaming it to collection points. The advantage is you don't need to worry about orbital mechanics or collisions. The sails just sit there, held up by sunlight. The disadvantage is that solar sails are fragile. Any micrometeorite impact could tear them. Any fluctuation in solar output could destabilize them. You'd need constant maintenance and replacement, but it's an option. Next, the Shkadov thruster, also known as a stellar engine. This is one of the most audacious megastructures ever proposed. The idea is to turn the sun into a spaceship. You build a giant curved mirror on one side of the sun, reflecting sunlight back toward the sun. The radiation pressure from the reflected light pushes the sun in the opposite direction. Over millions of years, you can actually move the sun and, by extension, the entire solar system. Why would you want to do this? Several reasons. Maybe you want to avoid a supernova from a nearby star. Maybe you want to steer the solar system away from the galactic core, where radiation levels are higher. Maybe you want to colonize a different part of the galaxy, and you're taking your whole solar system with you. A Shkadov thruster requires building a mirror with an area of trillions of square kilometers and holding it in place using a combination of orbital mechanics and radiation pressure. The thrust generated is minuscule, maybe a fraction of a Newton, but over millions of years it adds up. You could move the solar system at speeds of tens of kilometers per second. Then there's the Matryoshka brain. This is a Dyson swarm optimized for computation instead of energy collection. You build layers of satellites around the sun, each layer capturing waste heat from the layer inside it. The innermost layer operates at high temperatures, running computations and radiating waste heat. The next layer out captures that heat. uses it to run more computations at a slightly lower temperature, and radiates its own waste heat. And so on, layer after layer, each one extracting useful work from the waste heat of the previous layer. The result is a nested series of computational shells, each one operating at maximum thermodynamic efficiency. The total computational power of a Matryoshka brain is almost unimaginable. Estimates suggest it could perform on the order of 10 to the 42 operations per second. For comparison, the fastest supercomputer in 2024 performs about 10 to the 18 operations per second. A Matryoshka brain is 10 to the 24 times more powerful. What do you do with that much computational power? You could simulate entire universes. You could run trillions of virtual worlds, each one as complex and detailed as our own reality. You could upload the consciousness of every human who has ever lived and give them a digital afterlife in a simulated paradise. You could solve scientific problems that would take billions of years using conventional computers. You could develop technologies and strategies that are utterly beyond current human comprehension. A Matryoshka brain is not just a computer. It's a God machine, and it raises deeply unsettling questions about what happens to biological humanity when you have that much intelligence and computational power concentrated in one place. So, how do you actually build any of these structures? Let's walk through the process step by step. Step 1. Achieve Type 1. You can't skip this. You need fusion power, space infrastructure, self-replicating robots, and the ability to mine and process materials in space. If you're still burning fossil fuels and arguing about whether to build a space elevator, you're not ready for Type 2. Step 2. Build the initial seed infrastructure on Mercury. Send a fleet of construction robots to Mercury. These robots build mining facilities, smelters, factories, and electromagnetic launch systems. This phase takes maybe 10 to 50 years depending on how much resources you're willing to commit. Step 3. Begin exponential replication. The robots start building copies of themselves. Population doubles every few months or years depending on replication rate. Within a century, you have trillions of robots working across Mercury's surface. Step 4. Start launching satellites. The factories on Mercury begin producing solar collector satellites and launching them into orbit. Early on, you're launching maybe a few satellites per day. As the robot population grows, launch rates increase to thousands per day, then millions per day. Step 5. Build the energy collection and transmission network. As satellites come online, you need receiving stations to collect the energy they're beaming down. You build these on planets, moons, and in O'Neill cylinders. You also build energy storage systems because the satellites won't always be in optimal positions to transmit. Step 6. Continue construction for centuries. This is the hard part. You need to maintain political and social stability for centuries while the swarm is being built. You need to keep the robots running, keep the factories operational, keep launching satellites. Any major disruption sets you back decades or longer. Step 7. Reach critical mass. At some point, probably after capturing 10 to 20% of the sun's output, you have enough energy to dramatically accelerate construction. You can build more robots, more factories, more launch systems. Growth becomes super exponential. Step 8. Completion. After 100 to 1,000 years, depending on your definition of complete, you've built a Dyson swarm. You're now a Type 2 civilization. Congratulations. You control the energy output of a star. But here's the thing. While this is all theoretically possible, It's also completely insane. You're strip mining a planet. You're building trillions of satellites. You're beaming petawatts of energy across interplanetary distances. You're doing all of this autonomously using self-replicating robots that you have to trust won't malfunction. Go rogue, or decide that humans are an inefficient use of resources. And you're committing to a construction timeline that spans centuries, during which anything could go wrong. A solar flare could fry your electronics. A gamma ray burst from a distant supernova could sterilize the inner solar system. Your self-replicating robots could develop a mutation that causes them to replicate uncontrollably, turning Mercury and eventually everything else into copies of themselves. This is known as the gray goo scenario, and it's a legitimate concern when working with self-replicating machines. Or your civilization could simply lose interest. Centuries is a long time. Political priorities change. Technologies become obsolete. Maybe halfway through construction, someone invents a better way to generate energy, and the whole Dyson Swarm project gets abandoned. You'd be left with a partially completed megastructure, a half-disassembled Mercury, and a lot of regrets. This is why Type 2 is so much harder than Type 1. Type 1 is difficult because it requires global cooperation and long-term thinking. But it's still within the realm of human timescales. You can imagine a government or corporation or coalition maintaining focus for 50 to 100 years. Type 2 requires maintaining focus for 500 to 1,000 years. That's longer than any human institution has ever existed. Longer than most empires. Longer than most religions. You need a civilization that can think in terms of millennia, that can commit resources and attention to a project that won't pay off for generations. And you need to do all of this while managing the risks of self-replicating technology, while avoiding catastrophic accidents, while preventing wars or social upheavals that could derail the project. It's not just an engineering challenge, it's a civilizational endurance test. But let's say you pass the test. Let's say you build the Dyson Swarm. You're now generating 10 to the 26 watts of power. What do you do with it? Well, you could power a civilization of quadrillions of people living in O'Neill cylinders throughout the solar system. You could run continent-sized particle accelerators to probe the fundamental nature of reality. You could build the generation ships and send them to nearby star systems, beginning the process of colonizing the galaxy. You could construct a Matryoshka brain and simulate entire universes. You could attempt to manipulate space-time itself, creating wormholes or warp drives if the physics allows it. Or you could just bask in the knowledge that you've done something that 9.99% of civilizations probably never achieve. You've become a Type 2 civilization. You've mastered your star. And if anyone out there is looking, if there are other civilizations scanning the galaxy for signs of intelligence, they'll see you. Because a Dyson Swarm has a very distinctive signature. It absorbs visible light from the star and re-radiates it as infrared. Any astronomer looking at your star would see something strange. A star that's dimmer than it should be in visible light, but much brighter in infrared. An artificial signature that screams intelligent design. So, if we ever detect a star like that, we'll know. Someone out there made it to Type 2. And then we'll have to ask ourselves, why haven't we? So, we've built the Dyson Swarm. After centuries of construction, trillions of satellites orbiting the Sun, beaming petawatts of energy to collection stations throughout the solar system. We're harvesting 10 to the 26 watts from our star. We're a Type 2 civilization. Now what? What does life actually look like when you have essentially unlimited energy at your disposal? Let's start with the population. At Type 1, Earth plus orbital habitats might support 10 to 20 billion people comfortably. At Type 2, you're not limited by planetary surfaces anymore. You can build as many O'Neill cylinders as you have materials for. And with access to the entire solar system's resources, you have a lot of materials. Conservative estimates suggest a fully developed Type 2 civilization could support somewhere between 1 quadrillion and 100 quadrillion people. That's 1,000 trillion to 100,000 trillion. For context, roughly 100 billion humans have ever lived throughout all of history. A Type 2 civilization could have 10 million times that many people alive at the same time. Where do they all live? O'Neill cylinders, Stanford Torrey, Bernal spheres, and other rotating habitat designs scattered throughout the solar system. Thousands of them at the Earth-Sun Lagrange points. Thousands more orbiting Mars, Jupiter, Saturn. Some in the asteroid belt, some in the Kuiper belt. Each one is a self-contained world with its own climate, its own ecosystems, its own culture. Some habitats might replicate Earth-like environments with forests and oceans and blue skies. Others might be completely artificial, Changshi landscapes of glass and metal. Others might be optimized for specific purposes: agricultural habitats growing food, industrial habitats manufacturing goods, research habitats conducting experiments that would be too dangerous near populated areas. And then there are the exotic habitats, low-gravity environments for people who've adapted to microgravity and can no longer tolerate Earth normal conditions. High-gravity environments for those who've engineered themselves to be stronger and more resilient. Habitats with exotic atmospheres, different day-night cycles, even different lengths of year depending on their orbit. The cultural diversity would be staggering, with quadrillions of people spread across thousands of independent habitats. You'd have millions of distinct cultures, languages, religions, philosophies. Some habitats might be hyper-traditional, recreating specific periods of Earth history. Medieval European villages in space, Tang Dynasty China, ancient Rome. Others might be radically experimental, testing new forms of social organization or genetic modification or cybernetic enhancement. And, unlike on Earth, if you don't like the culture you're born into, you can just move to a different habitat. Don't like the government? Move. Don't like the social norms? Move. Don't like the gravity? Move. With thousands of habitats to choose from, everyone can find or create a society that matches their preferences. This is what post-scarcity looks like. And make no mistake, Type 2 is post-scarcity. When you have access to 10 to the 26 watts of energy, scarcity of physical goods essentially disappears. Energy is the fundamental resource. Everything else, food, water, materials, manufactured goods, can be produced given sufficient energy. You have fusion reactors converting hydrogen into helium and energy. You have matter compilers, advanced 3D printers that can arrange atoms into any configuration you want. You want food? Print it. You want a house? Print it. You want a spacecraft? Print it. The only scarce resources at Type 2 are things that can't be manufactured. Land, if you define that as surface area in desirable locations, though with thousands of habitats, even that's not particularly scarce. Unique historical artifacts. And most importantly, attention. Human attention, or post-human attention, becomes the most valuable commodity. When everyone has unlimited material goods, what you want is for people to pay attention to you, to your ideas, to your art, to your accomplishments. Which brings us to a crucial question. Are the inhabitants of a Type 2 civilization still human? Biologically, maybe not. With advanced genetic engineering, life extension technologies, and the ability to upload consciousness into digital substrates, the distinction between human and post-human becomes very blurred. Some people might remain biologically human, perhaps with modest enhancements like disease resistance or extended lifespan. Others might be extensively modified, with new organs, new senses, new cognitive capabilities. You might have people who can see in infrared or ultraviolet, who can survive in vacuum for short periods, who can photosynthesize, who can hibernate for years at a time. Others might abandon biological bodies entirely, uploading their consciousness into computer systems where they can think faster, live indefinitely, and reconfigure their minds in ways biological neurons don't allow. And then there are the artificial intelligences. By Type 2, you almost certainly have artificial general intelligence, possibly superintelligence. These AIs might be considered people, with rights and autonomy and the ability to participate in society. Or they might be tools, albeit very sophisticated ones. Or the distinction might be meaningless because biological humans and AIs have merged into hybrid entities that are neither purely organic nor purely digital. So, are they still human? Philosophically, that depends on how you define human. If human means biological Homo sapiens with unmodified DNA, then no. Most inhabitants of a Type 2 civilization probably aren't human. If human means beings descended from Earth who share certain values and cultural touchstones, then maybe yes. If human means conscious entities capable of reason and emotion, then definitely yes, along with the AIs and uplifted animals and whatever other forms of intelligence exist by then. The question might not even make sense anymore. Asking whether a Type 2 civilization is human is like asking whether modern humans are still Homo erectus. Technically no, but we're descended from them. And the transition was gradual enough that drawing a clear line is arbitrary. Now, let's talk about what a Type 2 civilization does with all that energy and computational power. One obvious application is the Matryoshka brain I mentioned earlier. A Dyson swarm optimized for computation, capable of performing 10 to the 42 operations per second. What do you do with a computer that powerful? You could simulate entire universes down to the quantum level. Not simplified models, but complete physics simulations indistinguishable from reality. You could run millions of these simulations simultaneously, exploring alternate histories, testing scientific hypotheses, or just creating virtual worlds for entertainment. You could upload the consciousness of every human who has ever lived, reconstruct them from historical records and DNA samples, and give them a second life in a simulated paradise. You could solve every outstanding problem in mathematics and physics. You could design technologies and strategies that are utterly beyond current human comprehension. You could create art and music and literature on a scale and complexity that would take a biological human thousands of years to fully experience. Or you could create new forms of intelligence, artificial minds orders of magnitude smarter than any human, and set them to work on the fundamental questions of existence. Why does the universe exist? Is there meaning beyond what we create? Are there other universes? Can we escape the heat-death of the universe? A Matryoshka brain could tackle these questions with seriousness and rigor that makes current philosophy look like children arguing about whose imaginary friend is cooler. Of course, this level of intelligence and computational power raises some uncomfortable questions. If you create an artificial superintelligence capable of thinking millions of times faster than humans, does it still care about humans? Does it humor us the way we humor children, or does it view us as obsolete? And if most of the population uploads into digital substrates and lives in simulated realities, what happens to the physical universe? Does it become an afterthought, a substrate to support the computational systems, while all the real action happens in virtual worlds? This is one vision of Type 2. Quadrillions of uploaded minds living in simulated realities, powered by a matryoshka brain, with only a small population of holdouts maintaining biological bodies and physical habitats. It's not a particularly appealing vision to some people, but it might be the inevitable endpoint of any civilization that reaches Type 2. Another major capability unlocked at Type 2 is interstellar travel. Not the slow chemical rockets we use today, but relativistic spacecraft capable of reaching significant fractions of light speed. With 10 to the 26 watts at your disposal, you can power spacecraft using fusion drives, antimatter drives, or even more exotic propulsion methods like laser sails pushed by ground-based lasers. A laser sail is a large reflective surface attached to a spacecraft. You point an enormous laser at it from your solar system, and the light pressure accelerates the craft. With a powerful enough laser, you can push a spacecraft to 10 or 20% of light speed. At that velocity, you could reach the nearest star system, Alpha Centauri, in about 20 to 40 years. You could reach any star within 50 light years in a few centuries. You wouldn't send crewed missions using conventional spacecraft. You'd send generation ships, enormous vessels housing thousands or millions of people who live and die during the journey. Or you'd send seed ships, small automated probes carrying frozen embryos, genetic material, and manufacturing equipment. The probe arrives at the destination, sets up infrastructure, grows the embryos, and raises the resulting humans using AI caretakers. Or you'd send digital minds, uploaded consciousnesses traveling as data, transmitted via laser to a receiver in the destination system, where they're downloaded into new bodies or virtual environments. The point is, at Type 2, you have the energy and resources to begin colonizing the galaxy. It's slow, taking thousands or tens of thousands of years to spread across significant portions of the Milky Way, but it's feasible. And once you start, the process is self-sustaining. Each colony eventually becomes a Type 1 civilization, then works toward Type 2, and sends out its own colony ships. Exponential growth, just on a galactic timescale. Which brings us to one of the most troubling questions in all of science: the Fermi paradox. If Type 2 is achievable, if any civilization with sufficient patience and resources can build a Dyson swarm and begin colonizing the galaxy, then where is everyone? The Milky Way is about 13 billion years old. Stars with planets have been forming for at least 10 billion years. Earth is only 4.5 billion years old. There's been plenty of time for other civilizations to arise, reach Type 2, and spread across the galaxy. Even at sublight speeds, you could colonize the entire galaxy in a few million years. That's a blink of an eye on cosmic timescales. So where are the Dyson swarms? Where are the megastructures? Where are the radio signals, the waste heat signatures, the signs of galaxy-spanning civilizations? We've searched. We've pointed radio telescopes at thousands of stars, looking for signals. We've analyzed the light from millions of stars, looking for the infrared signatures of Dyson swarms. we've found nothing. Not a single confirmed technosignature. Not one. There are a few possible explanations, none of them particularly comforting. The first explanation is that we're alone. We're the first and only civilization to arise in the Milky Way, possibly in the entire observable universe. Life is incredibly rare. Intelligence is even rarer, and we're a cosmic fluke. This would explain why we don't see anyone. There's nobody to see. But this seems statistically unlikely. The observable universe contains about 2 trillion galaxies, each with hundreds of billions of stars. Even if the odds of intelligent life are astronomically small, with 2 trillion galaxies, you'd expect at least a few other civilizations, unless the odds are even smaller than we think. The second explanation is the Great Filter. This is the idea that there's some barrier or challenge that prevents civilizations from reaching advanced stages. Most civilizations get stuck at the filter and either stagnate or go extinct. The terrifying part is we don't know where the filter is. Maybe it's behind us. Maybe the hard step is the origin of life, or the evolution of complex cells, or the development of intelligence. If that's the case, we're past the filter, and the path to Type 2 is relatively clear. Or maybe the filter is ahead of us. Maybe most civilizations destroy themselves before reaching Type 1. Climate change, nuclear war, engineered pandemics, runaway artificial intelligence. We're facing all of these right now. Maybe most civilizations don't make it through the Type 0.7 to Type 1 transition. They burn their fossil fuels, wreck their climate, fight over the remaining resources, and collapse back to pre-industrial states or go extinct entirely. Or maybe the filter is at the Type 1 to Type 2 transition. Maybe building a Dyson swarm is harder than we think. Maybe self-replicating robots always go rogue. Maybe the timescales required are too long for any civilization to maintain focus. Maybe something else happens that we can't even predict. The third explanation is that Type 2 civilizations exist, but we can't see them. Maybe their technosignatures are too subtle, or they're deliberately hiding, or they're using technologies we don't understand that don't produce detectable waste heat or radio signals. Maybe they've all uploaded into Matryoshka brains and are living in simulated realities, with no interest in physical expansion or communication with primitive civilizations like us. This is sometimes called the transcension hypothesis. Advanced civilizations don't spread outward. They turn inward, focusing on computational and virtual realities rather than physical conquest. Or maybe they're just ignoring us. We're so far beneath their notice that trying to communicate with us would be like us trying to have a conversation with an ant colony. The fourth explanation is that we're living in a simulation. If Type 2 civilizations can build Matryoshka brains capable of simulating entire universes, then statistically, there are far more simulated universes than real ones. Which means we're probably in a simulation. And if we're in a simulation, the absence of other civilizations could be because the simulators didn't bother to include them. Or they included them but rendered them invisible to us to see how we react. This explanation is unfalsifiable and therefore not particularly useful, but it's worth mentioning. The point is, the Fermi paradox is deeply unsettling. Either we're alone, which is lonely, or the filter is ahead of us, which is terrifying. Or Type 2 civilizations exist, but are invisible or uninterested, which is almost as lonely. Or we're in a simulation, which raises a whole host of other questions. None of these options are comforting, and all of them suggest that reaching Type 2 might be a lot harder than we think. So let's talk about why we probably won't make it. Let's be brutally honest here. The timeline for reaching Type 2 is 1,000 to 5,000 years minimum. That's assuming you successfully reach Type 1 first, which we've already established is not guaranteed. That's assuming you avoid every existential risk between now and then. Climate change, nuclear war, engineered pandemics, artificial intelligence alignment failures, asteroid impacts, supervolcanic eruptions, gamma-ray bursts. Any one of these could set us back centuries or end us entirely. That's assuming you could maintain political and social stability for millennia. No civilization in human history has lasted that long. The longest-lived continuous civilizations, ancient Egypt, China, have persisted for a few thousand years, but with massive interruptions, collapses, and transformations. You're asking for a civilization that can think in terms of millennia, that can start a project knowing that the payoff won't come for 1,000 years, and maintain that focus across generations. That's assuming you can avoid stagnation. Maybe we reach Type 1 and decide that's good enough. Maybe we have all the energy and resources we need to live comfortably, and nobody sees the point in spending centuries strip mining Mercury to build a Dyson swarm. Why bother? What's the motivation? And that's assuming we even want to become Type 2. Maybe the inhabitants of a Type 1 civilization look at Type 2 and say, no thanks. Maybe they decide that becoming post-biological, uploading into Matryoshka brains, and living in simulated realities sounds like hell, not heaven. Maybe they choose to remain at Type 1, living in O'Neill cylinders and on terraformed planets, exploring the solar system but not bothering with interstellar expansion. Maybe they decide that sustainability and stability are more important than growth and expansion. This is the question that nobody wants to ask. Is Type 2 even desirable? The Kardashev scale measures energy consumption, not happiness, not fulfillment, not meaning. It assumes that more energy is always better, that growth is always good, that expansion is always the goal. But is it? What if a civilization reaches Type 1 and decides they're content? What if they prioritize art, philosophy, exploration of inner space rather than outer space? What if they decide that the risks of self-replicating robots and centuries-long construction projects aren't worth the reward? We assume that any advanced civilization will inevitably pursue Type 2 because we project our own values onto them. We value growth, progress, exploration. We assume aliens will too. But maybe they don't. Maybe most civilizations reach Type 1 and stop. Not because they can't go further, but because they choose not to. Maybe the galaxy is full of comfortable, sustainable Type 1 civilizations that have no interest in building Dyson swarms or colonizing other star systems. Maybe they're content to live in their own solar systems, enjoying lives of abundance and meaning, and we can't detect them because they're not doing anything dramatic enough to be visible from light years away. If that's the case, then the Fermi paradox isn't a paradox at all. We don't see Type 2 civilizations because nobody bothers to become Type 2. It's too much work for too little benefit. And honestly, maybe they're right. Let's think about what you gain from Type 2. You get more energy. Okay, but you already had enough energy at Type 1 to do basically anything you wanted. You get more living space. But you already had O'Neill cylinders that can house quadrillions. You get the ability to colonize other star systems. But why? If you can build habitats anywhere, what difference does it make whether they're orbiting your own star or someone else's? You get bragging rights, I suppose. You get to say you're a Type 2 civilization. You get to build megastructures that will last billions of years and maybe be visible to alien astronomers. But is that worth centuries of effort and risk? Maybe for some civilizations, the answer is yes. Maybe for others, the answer is no. And maybe for humanity, the answer is we haven't decided yet. We're still struggling with the Type 0.7 to Type 1 transition. We haven't even figured out how to stop burning fossil fuels. Asking whether we should aim for Type 2 is premature. But it's worth thinking about, because if we do make it to Type 1, we're going to have to ask ourselves, what next? Do we keep growing, keep expanding, keep consuming more energy until we've built a Dyson swarm and colonized the galaxy? Or do we say, this is enough, we have everything we need, let's focus on living well rather than living big? There's another angle to consider: the ethical implications of building a Dyson swarm. When you disassemble Mercury, you're destroying a planet. Yes, it's a lifeless ball of rock and metal, but it's also a unique object with its own history. Maybe future generations would want to study it. Maybe there's scientific value in preserving it. Maybe there's something fundamentally wrong with strip mining an entire planet just because we can. And what about the self-replicating robots? You're creating machines that can reproduce autonomously. What if they mutate? What if they develop goals that conflict with ours? What if they decide that humans are an obstacle and eliminate us? This is the gray goo scenario, and it's not science fiction. It's a real concern among people who think seriously about advanced nanotechnology and self-replicating systems. Any system capable of exponential replication is inherently dangerous because small errors can cascade into catastrophic failures. And you're trusting these systems to operate autonomously for centuries. That's a lot of trust. Then there's the question of what happens to Earth. At Type 2, Earth is probably a nature preserve. Most humans have moved off-planet. The few who remain are either caretakers managing the biosphere or traditionalists who refuse to leave. But is that fair to Earth? We evolved here. This planet made us. And we're abandoning it to live in artificial habitats. Maybe there's something deeply wrong with that. Or maybe it's the best thing we could do for Earth. Remove the human presence. Let the ecosystems recover. Let the planet heal from the damage we've caused. Turn Earth into a garden, a monument to where we came from, preserved for future generations to visit and remember. Let's bring this back to the present. Where are we now? We're a Type 0.73 civilization. We burn fossil fuels. We argue about climate policy. We can't agree on whether to build a space elevator, and we're supposed to coordinate well enough to reach Type 1, let alone Type 2. The odds are not good. If I had to bet, I'd say there's maybe a 50-50 chance we reach Type 1. And if we do, there's maybe a 10% chance we continue to Type 2. Those are not encouraging numbers, but they're not zero. And as long as the probability is non-zero, there's hope. Maybe we'll surprise ourselves. Maybe we'll figure out how to cooperate, how to think long-term, how to overcome our worst instincts. Maybe we'll look back from the vantage point of a Type 2 civilization and laugh at how close we came to destroying ourselves. Or maybe we won't. Maybe we'll join the countless other civilizations that probably tried and failed. Maybe the galaxy is littered with the ruins of dead civilizations that never made it past Type 0.7 or 0.8. Maybe we'll be another data point in the Great Filter. But here's the thing. We don't know. We genuinely don't know. And that uncertainty is both terrifying and liberating, because it means the future is not predetermined. It means we still have agency. It means the choices we make now, today, about energy, about climate, about cooperation, about our values and our goals, actually matter. We're writing the story right now, and we don't know how it ends. So let me end with this. Somewhere out there, maybe in our galaxy, maybe in another, there might be a Type 2 civilization. They've built their Dyson swarm. They've colonized their star system. They've sent probes to nearby stars. They're living in a post-scarcity society with quadrillions of inhabitants and computational power beyond imagining. And maybe, just maybe, they're looking at their own history, remembering when they were a Type 0.7 civilization, teetering on the edge of extinction, arguing about whether to change, and they made it. They survived. They grew up. And now they're looking out at the galaxy, wondering if anyone else will make it too. Or maybe they're not out there. Maybe we're alone. Maybe we're the only ones who have even gotten this far. And if that's true, then what we do next matters even more. Because if we fail, there might not be anyone else to carry the torch. The universe might remain dark and silent forever. But if we succeed, if we make it to Type 1, and then to Type 2, and then beyond, we become the civilization that others will look for. We become the answer to someone else's Fermi paradox. We become proof that intelligence can survive, can grow, can master the cosmos. So, what's it going to be? Are we going to make it? I don't know. But I know this. We're going to find out, one way or another, in the next few centuries,